Welcome to Math TV with Professor V. This video lecture is for linear algebra, section 1.1 on Introduction to Systems of Linear Equations. If you're an algebra or precalculus student, this video is not for you. I'll link other videos I have on my channel on solving systems of linear equations here, but this is for advanced calculus students who are taking linear algebra. All right, so definition. A linear equation in n variables. Notice we're keeping the number of variables arbitrary, so we denote them with subscripts. We're not going to do x, y, z so much. We do x1, x2, x3, up to xn. It has the form a1x1 plus a2x2 plus a3x3 all the way up to anxn is equal to b. That's a linear equation. What makes it linear? All of the variables, x1, x2, x3, are raised to the first power. Nothing higher, nothing else. No rational exponents that are not integers or not 1, bottom line. The coefficients, a1, a2, a3, up to an are real numbers, and the constant term b is a real number. The number a1 is the leading coefficient and x1 is the leading variable. So what we're going to look at now is a system of linear equations. And we say we have a system of m linear equations in n variables when we have a set of equations, each of which is linear in the same n variables. So notice here's the system. We usually denote it by putting these braces here on one side, and you have each linear equation. Now notice we have double subscripts going on. Whoa, whoa, whoa. Okay, this is for equation 1. This is variable x11, x12, x13, etc. up to x1n. Remember, we have n variables. So this first one is telling me these are from equation, the equation 1. And then the second number in the subscript tells you which variable it is. So you notice all of these start with 2's because they're in the second equation in the system. And then this 1, 2, 3 up to n, those are the variables. And then here, this is the mth equation. So we have m many equations with n variables. And then they're equal to the constants b1 through bm. Okay, so basically just keep in mind m represents the number of equations in the system, and then amn, that is the constant or coefficient in row m, column n. All right. Obviously, we're going to want to solve these systems of linear equations. So what does a solution look like? A solution is a sequence of numbers, s1, s2, s3, up to s sub n, that is a solution of each equation in the system. So a solution must satisfy every single equation in the system. All right. Now, we classify systems of linear equations depending on their solution sets. So a system of linear equations is consistent when it has at least one solution, and then we call it inconsistent when it has no solution. So consistent systems can have either exactly one solution, or they could have infinitely many solutions. The way I think of it is it's called consistent if the solution set consists of something. That's not really where it comes from, but that just helps me remember. And then a solution set is called inconsistent when there's no solution. And we'll look at some cases like that. All right. For a system of linear equations, exactly one of the statements below is true. So here are your options basically when you're solving. You can have only one of 3 possible scenarios. First scenario, the system has exactly one solution, one unique solution, and it's consistent. Option 2, the system has infinitely many solutions, Still a consistent system. Option 3, the system has no solution, making it inconsistent. All right. And you've probably classified these before in some of your more elementary math courses, so this terminology should be a bit of a review. Now we're going to get into a certain form or pattern that we want to manipulate our systems of equations into. And we say a system is in row-echelon form if it has a stair-step pattern with leading coefficients of 1. So basically, I'll show you how it's going to look, but you want to have just the leading terms remaining, zero out everything else, much like if you've worked with some matrices before. We'll get into that in the next video, but it's the same idea. And then all those A11s, the leading coefficient needs to be a 1. Okay, two systems of linear equations are equivalent when they have the same solution set. So to solve a system that is not in row-echelon form, first rewrite it as an equivalent system that is in row-echelon form using the operations listed below. So here's your 3 options, okay? You can't add to this list. This is it. You can interchange 2 equations. You can multiply an equation by a non-zero constant, or you can add a multiple of an equation to another equation. So we're going to work through some examples so you can see how to do this. And rewriting a system of linear equations in row-echelon form usually involves a chain of equivalent systems, using one of the 3 basic operations to obtain each system. And this whole process is called Gaussian elimination. So these are terms that you're going to have to get used to, because oftentimes directions will either ask you to use Gaussian elimination or rewrite a system in row-echelon form, and you need to know what that means, okay? So let's just jump into an example. First one states, use elimination to rewrite a system in row-echelon form, aka use Gaussian elimination. So you guys, this means the same thing. Your brain needs to understand that these two are telling you to do the same process, okay? So first things first, I want the coefficient for x1 here in my first equation to be a 1, okay? So how can I make that 2 a 1 only using one of the 3 operations here? Well, I could interchange 2 rows. That's not going to help me. I can multiply an equation by a non-zero constant. Okay, that's going to work, because to make that 2 a 1, if I multiplied that first row by a half, that would do it. So you want to indicate whatever operation you're doing so that you can go back and recall what happened. So I'm going to take 1/2, that's my non-zero constant, multiply it by row 1. This is row 1, this is row 2, this is row 3. And that's going to become my new row 1. I like to use capital letters. A lot of textbooks do that to show that that's what the new row is going to be, and then the lowercase is what the previous rows are. Okay, so let's go ahead and do that first. So if I multiply all of row 1 by a half, now it just becomes x1 plus 1/2 x2 minus 3/2 x3 equals 2. And then I'm not touching the other rows, so we have 4x1 plus 2x3 equals 10. And then negative 2x1 plus 3x2 minus 13x3 equals negative 8. Okay, so the stair-step pattern that we're looking for is now I want to have zeros underneath the rest of the first column, underneath all of the entries that lie beneath x1. And to accomplish this without undoing the work that you just did in the previous step, you have to follow this process. You're going to use this entry here, this x1 in the top left, that whatever entry you just made a 1, you use it to zero out the entries beneath. So I'm going to use this third operation here, add a multiple of an equation to another equation. So I think to myself, what do I wish this was so that if I were to add it to this row, I would get a 0 here? If this was negative 4x1, I'd be in business. So that's precisely what we're going to do. I'm going to take negative 4 times my current row 1, add it to my current row 2, and that becomes my new row 2. You always multiply your non-zero constant by the row that you just created that 1 in. It's a pivot when we talk about matrices in the next video. You add it to some other row. You don't multiply that row by anything, okay? And then that's the row that gets replaced, the one that doesn't get multiplied by a non-zero constant. Okay, so let's see how that's going to go. Negative 4 times row 1. If you need to do some scratch work, that's totally fine, okay? So negative 4 times row 1, that would give me negative 4x1 minus 2x2 plus 6x3 equals negative 8. And then row 2 is here, 4x1 plus 2x3 equals 10. So let's add them together. And I'll just write the result here. This is my new row 2. So notice these will cancel. I'll just have negative 2x2 plus 8x3 equals 2. Okay, so leave a space. I'm not going to change my row 1, so let me rewrite that now. That's staying as is. And then my new row 2 is right here. So we've got negative 2x2 plus 8x3 is equal to 2. Beautiful. And then again, I want to repeat a similar process so I can make a 0 appear here at this entry. So how would you do that? Using this x1, using that top row. Well, I really wish that this was a 2x1. That way I could add it to that third row and create a 0. So that's what we're going to do. I'm going to take 2 times row 1, add it to row 3, and that's my new row 3. All right, let's do a little scratch work off to the side. And then when you get good, you don't need to do the scratch work. So 2 row 1 is 2x1 plus x2 minus 3x3 equals 4. Here's row 3, negative 2x1 plus 3x2 minus 13x3 equals negative 8. Add them together. This is my new row 3. So this is gone. Then we have 4x2 minus 16x3 equals negative 4. So let's add that in here. So 4x2 minus 16x3 equals negative 4. All right, good. So basically this whole column's taken care of. Then I move my attention to the leading entry here in the second row. So this coefficient now I'm going to try to make it a 1. How do you do that? Best bet when you're trying to make a 1 is this operation here, multiply an equation by a non-zero constant. That's the best way to make 1s most of the time. So how are we going to do that? How do I make that negative 2 a 1? I'm going to multiply row 2 by a negative 1/2, and then that's going to be my new row 2. Okay, so let me rewrite row 1 first. x1 plus 1/2 x2 minus 3/2 x3 equals 2. And then once I've multiplied row 2 by negative 1/2, now this is just x2 minus 4x3 equals negative 1. And then I'll leave this alone for now. Okay. Beautiful. Now what do we try to do? Well, similar to before, I'm going to use this x2 to make zeros in the entries above and below it in that column. So I want there to be a 0 here, and I want there to be a 0 down here. Okay, so how do we do that? Let's see. Using row 2, I'm going to take negative 1/2 times row 2, add it to row 1. That's my new row 1. And then to make a 0 down here, I'm going to have to multiply this row by -4 plus row 3 is my new row 3. Good? Okay. I'm not going to do scratch work on this one. Let's see if we can handle it in our head. So this x1 is going to stay the same. There's no x2. If I multiply -4x3 by -1/2, now I have positive 2x3 minus 3/2 is going to give me a positive 1/2 x3. And then again, I'm multiplying this by -1/2, so now it's positive 1/2 plus 2, that's 5/2. I'm not changing row 2, that's staying the same. And then now let's see, I'm taking -4 times row 2, adding it to row 3, so that's a 0. -4 times -4x3 is positive 16x3. Add that here, I get a 0. What? Okay, so we've got all zeros on the left-hand side there. And then, don't forget about this constant, -4 times -4. That's gonna, oh, here. -4 times -1 is positive 4. Times -4 is 0. Ooh, this is a little bit funky. What do you do here? You pretty much stop, okay? At this point, I notice I have no variables on the left-hand side of this third equation. I have a 0. So now you're going to look at the right-hand side. Since I have a 0 again, 0 equaling 0, that is a true statement. This is an identity. So when that occurs, that's an indication that we have an infinite number of solutions. Okay? And so what you want to do from here, the way you write your final answer, is you rewrite the variables on the furthest left in terms of the other variables. So I'll show you what I mean by that. So which variable is on the furthest left in that first row? It's x1. So I'm going to solve or isolate x1 in terms of, it looks like x3. So x1 is equal to -1/2 x3 plus 5/2. And then do the same thing for the second equation. x2 is equal to 4x3 minus 1. So notice, this is basically why you have an infinite number of solutions. I don't have any information about what x3 needs to be, but I can define x1 and x2 in terms of x3. So x3 can take on any real number value, and then I can find x1 and x2 afterwards so that they satisfy the system of equations. So the solution, how do you finally write it out? Not like this. The solution of the system is as follows. It's an ordered triple, right? We had 3 variables, x1, x2, x3. So x1, I have it defined up above. It's -1/2 x3 plus 5/2. x2 is 4x3 minus 1. And x3 is itself, x3. So we say that x3 is a free variable. The other 2 variables are defined in terms of it. So it means it can be any real number. And then you would find x1 and x2 based on what x3 is equal to. And then another way that you can write this out is as follows. So later on we'll see how this ties in with what you've learned perhaps in other math classes. So notice I have a constant times x3, a constant times x3, a constant times x3. So I can basically extract the x3 out. I can factor it. And then we just have a plain constant here, and a 0. So the idea is I could write it as x1, x2, x3, where if I factor out the coefficients of x3 from each of the coordinates, you'd have a -1/2 in the first one, a 4 in the second, and a 1. These are all multiplied by x3, plus the constants are 5/2, -1, and 0. So basically, if you were to distribute this back out, add it to this ordered triple, you would get back the original. And there's a purpose to writing it this way, which we'll study more later, okay? So to summarize, remember there were 3 possible scenarios when you're solving systems of equations, and this is one of the ones where we had an infinite number of solutions. So what helped us conclude that we had an infinite number of solutions? We had a true statement result in one of our equations. For example, we had 0 = 0. You could alternatively have like 5 = 5, 2 = 2, same thing. The other possible scenario that we haven't run into yet is if you were to have no solution, and that would be if we had a false statement arise in one of our equations in the system. So a false statement would look like 0 equaling any other number besides 0. Then that would be a false statement, which would mean that you have no solution to the system. The other thing that occurs at times is you'll notice you'll have less equations than you have variables. And when that happens, then that means you either have no solution or you have an infinite number of solutions. But you won't have exactly one, okay? Good. So let's kind of explore a little bit with having no solution to the system, okay? And the example asks us to find the value or values of k such that the system of linear equations has no solution. So basically they want it so that you end up with some sort of false statement when you're performing Gaussian elimination. You end up with a false statement. Okay. So what I'm going to do is go through the process just like last time of Gaussian elimination. So remember, we want that leading coefficient to be a 1 in that first row, which it already is. Fabulous. And then I'm going to use this entry here to make all of the entries below it or above it zeros. So there's only one entry I have to worry about. I need that 3x1 to be gone. So what would I do? I would take -3 times row 1, add it to row 2, and that would be my new row 2. So let's see what we got going on now. Row 1's not changing. x1 plus 2x2 plus kx3 = 6. And then now -3 times row 1, that would be a 0. -3 times 2x2, I'm looking right here, guys. That would be -6x2 plus 6x2. Okay, that's a 0 also. And then -3 times kx3 would be -3 kx3 plus 8x3. And this would equal, now let's take care of the constant, -3 times 6, that's -18, plus 4 is -14. Okay, to more succinctly write it, let me just factor out the coefficients on x3 here. So x1 plus 2x2 plus kx3 = 6. And then I have -3k plus 8 times x3 = -14. Okay, so here's the idea, because they want us to figure out what k needs to be so that we have no solution. To get no solution, we want the coefficient of x3 to be 0. Why is that what we want? Because if this is a 0, then we would have a false statement, because then we would have created an equation that states that 0 equals -14, which is total garbaggio. So how can we guarantee that the coefficient of x3 is 0? Well, what we want is for -3k plus 8 to be equal to 0, so we require negative 3k equal negative 8. So k equaling 8/3 would create an inconsistent system with no solutions. Okay, so that concludes the video. It is a little weird doing Gaussian elimination on systems of linear equations. Usually we use it for matrices. So if you're frustrated with this section, I totally get it because it feels super inefficient to be writing out these variables if you've done this process before with matrices, but I promise that's coming next and we won't have to keep doing it this way and torturing ourselves. But just stay tuned. Lots of more linear algebra videos coming your way, so subscribe if you haven't already. And I'll also link the sign up for my Patreon here. I'm solving the homework sections from Calc 1, 2, and 3 on that at the moment. And I have a special introductory promo for just $4.99 a month, which expires at the end of August 2022. So if you haven't signed up already, do so, because it'll be a great resource as you're working through your homework in your classes. So thanks for watching. Give the video a thumbs up, subscribe if you haven't already, and stay tuned.